Today we're going to talk about ionic bonding, or maybe a little bit more specifically, nomenclature of ionically bonded compounds. When we're talking about ionic bonding, what we're talking about is the complete transfer of electrons from one species to another. This is different than covalent bonding, where atoms will share electrons. So in this case, we have two particular atoms, say a sodium atom and a chlorine atom. And the sodium atom will give an electron to the chlorine, and then sodium will be positively charged, chlorine will be negatively charged, and you can have an attractive interaction between those ions to create an ionic bonded compound. And these structures typically have very ordered patterns, and we'll talk about the patterns and the packing and all of this sort of stuff later. But what we want to focus on now is what kind of ions we would expect for different elements on the periodic table and how we name ionically bonded compounds. So here's a diagram of the periodic table, the main group ions. So in the middle, we've removed the transition metals. So you have the alkali metals here in the first column, the alkaline earth elements, and then over into the P block, ending with the noble gases in column 18 or 8A. And what you can see is there are the typical charges for the alkali metals in column 1 are +1. So when they lose one electron, their electronic structure looks like a noble gas, which is favorable. The alkali earth metals, starting with beryllium going down, have a typical charge of 2+. Moving over to the other side, the elements that are nearer to the noble gases in columns 15, 16, and 17, prefer to gain electrons to look like the noble gases. So it's important to know the typical charge states for these compounds. Now, it's also important to know how we name these ionic compounds. So as an example, if we have lithium oxide, so we're going to have lithium, which likes to have a +1 charge, combined with oxygen, which likes to have a -2 charge, so gain 2 electrons. And so, of course, to balance the total charge, we're going to need to have 2 lithium 1+ ions and 1 oxygen 2- ion to make Li2O. So the subscript 2 denotes that there are 2 lithiums there. Now notice the name for this, the positively charged thing, which we call the cation, is just the elemental name, so lithium. And notice it's lowercase, this is not a proper noun. And the anion, which is the negatively charged thing, we've changed the ending. It's not oxygen, we write oxide. So this ionic compound, Li2O, is named lithium oxide. Now, continuing this, say we have calcium and sulfur together. Well, calcium likes to be 2+. Okay, sulfur likes to have 2-. So we just need one of each to balance the charge. So we have CaS, and we call this, again, calcium sulfide. So again, this IDE ending, we've changed the element to have this IDE ending. Okay, so now we can look and do other things if we're given the name to provide the chemical formula from the name. So let's start with sodium sulfide. So sodium likes to have +1. Okay, and sulfide again is S2-. Okay, so we're going to have 2 sodiums and 1 sulfide. Okay, now we can have calcium bromide, so calcium is Ca2+. All right, bromine over here is a halogen, so that's Br-. So in this case, we're going to have 2 of the bromines, so CaBr2. Okay, so that would be the chemical formula for calcium bromide. So you are expected to know the names and charge states of all of these cations and anions, and know that when you have these binary compounds, that the ending for the chemical name has this IDE ending. Okay, so you need to know that you change the elemental name to IDE. So those are things that you need to know. Now let's go back to what we cut out in the first place, specifically the transition metals. In this case, it gets a little bit more rich in terms of the charge states that are possible. So when we add these d electrons, we can have multiple charge states. And what's shown here in this short snippet of the periodic table is not an extensive list of all of the possible charge states, but it's kind of an introduction. And so what we need to do, because these elements can have multiple charge states, we need to denote what the particular charge state is. So for example, iron can be 2+ or 3+. So if we give the name, we can't just say iron oxide, because we don't know if it's iron 2+ or iron 3+. So we need to denote that. So if we want to give the chemical name from the symbol, so if we have MnO, we know that oxygen likes to be 2-. So in that case, since we only have one manganese, it has to be 2+. Okay, so we have manganese 2+ and oxygen 2-. So what we can do is we write the element name, manganese, just like we would. And in parentheses, in Roman numerals, we put the charge state. So it's +2, so it's going to be manganese 2, again, IDE, oxide. So manganese 2 oxide. Okay. In the same way, we have CuCl, so this is copper chloride. Okay, so copper. And in this case, we know that the chlorine has a -1 charge, so it's copper 1 chloride. And in this case, we have 2 chlorine ions. And so we have copper 2, because it's 2+, because we have 2 of the chloride ions. So with these transition metals, you need to make sure that you denote what we call the oxidation state or the charge state is for those species. Okay. In the same way, we can have we can provide the chemical formula. So chromium 3 chloride. Okay, so chromium 3+ chloride. Each of them is a 1-, so CrCl3. Okay. Now, most of the species that we look at have these Roman numerals, and that's all I expect you to know. However, it's also very common in different places, depending on where you're reading, to use Latin nomenclature to denote the charge state for upper and lower. So in this case with iron, if we look at, so we can have iron 2+ or iron 3+, okay? And so if we'd write this as a name, this would be iron 2, this would be iron 3. However, there's Latin nomenclature that uses different endings, okay? Okay, ferrous or ferric. Okay, so we change the ending, so we use the Latin prefix for iron, and then for the lower charge state it has an OUS ending, and for the higher charge state it has an IC ending. And this is common when you have other elements as well. So for example, copper can be +1 or +2, so you can have cuprous or cupric ions. Again, you don't need to know this, but you may see it around from time to time, so it's good to understand these Latin endings. So ferrous means iron 2, so this would be FeBr2. And this is equivalent to writing it as iron 2 bromide, so these are both identical. So again, I don't expect you to know this Latin nomenclature with the OUS or the IC ending, but you might see it around. However, you are required to know that with transition metals, you need to provide the correct charge state or oxidation state using Roman numerals. Okay, so looking at this again, we have what are called binary ionic compounds, which are just 2 particular atoms that have been ionized that combine together to make an ionic compound. Okay, so just looking at this again, sodium chloride. Na+, Cl- makes NaCl. Magnesium oxide. Magnesium likes to be 2+, oxygen likes to be 2-, so we make MgO. All right. Then you need to make sure, again, that we balance charge states. So here's a couple more fleshed out examples of how charge states can be balanced. So if you have aluminum sulfide, aluminum likes to be +3. Okay, sulfur likes to be -2. In order to balance the charge states, you're going to need 6+ and 6-. That's the lowest common multiple of both of those. So you're going to have 2 aluminums to make 6+, and 3 of the sulfides to make 6-. So you're going to have Al2S3. Okay, and you can look at the other examples for iron 3 oxide, okay, tin 2 chloride, or lead 2 fluoride. Okay, so you need to make sure that you balance the charge by adding the sufficient number of cations or anions of interest in that ionic compound. Okay, the next thing that we need to cover is polyatomic ions. So these are ions that are bonded together, not by ionic forces, but by covalent forces. And we'll talk about how these things come to be in terms of bonding together later. But the point here is we have these really common ions, polyatomic, so many atom ions that we encounter a lot. And in order to speak this language together, we need to have this foundational background in terms of when I say ammonium, you know I mean NH4 plus. And so you need to know all of these polyatomic ions. Okay, notice there's a lot of common things together. So if we look at this family right here, okay, so ClO minus, so chlorine with 1 oxygen, chlorine with 2 oxygens, all the way up to chlorine with 4 oxygens. Okay, as we add oxygens, we go from an ITE ending to an ATE ending. So we go from chlorite to chlorate. And this is very common as you add oxygens. Okay, so if we look, for example, up here, we have NO2 minus, which is nitrite, NO3 minus, so we've added 1 oxygen, nitrate. Okay, so if you notice all of that, a lot of these things, it becomes much simpler in terms of just looking at the change of that suffix. Again, sulfite, sulfate for SO3 2 minus, SO4 2 minus. Okay. All right, and then as you go further, if you take, in this case of the chlorite, we can add or remove even more oxygens. So we have hypochlorite if we have just 1 oxygen, and perchlorate if we have 4 oxygens. Okay, so in addition to changing the suffix, we can add a prefix if we're removing or adding more oxygens. Okay, so I encourage you to just sit down and look at this table and know all of these things. These are very important to know when we're talking this language of chemistry. Now, the nice thing about these polyatomic ions is if you have compounds where these polyatomic ions are in ionically bonded compounds, you just use these names. So as an example, in the upper left-hand corner, if we have ammonium chloride, right? So ammonia, the ammonium ion is NH4 plus. That can, of course, combine with a chloride ion to make ammonium chloride, okay? And we don't change the name of these polyatomic ions. In this case, it's the cation, the positively charged thing, okay? So that's just ammonium. And then chloride, again, we have changed, right? So this is just chlorine. And we know if that's an anion, we have to change the ending to IDE. However, if we have something like this, CaCO3, so CO3 2 minus is carbonate, okay? So that's right there. So we have Ca2 plus and CO3 2 minus. So the anion is calcium, the cation is carbonate, and we do not change the name or change anything with the carbonate. So the name of that is calcium carbonate. Okay, cool. So if we want to put the chemical formula for a few different things, so sodium nitrate, so sodium again likes to be plus, nitrate is NO3 minus if we look at our table. Okay, so this is going to be NaNO3. Okay, so that's the chemical formula. Now we have potassium sulfate. Potassium likes to be 1 plus. Sulfate is SO4 2 minus. So we're going to have 2 potassiums to balance and make that sulfate, the potassium sulfate. So again, you're expected to know the names, charges, and formulas of all the polyatomic ions in this table. And a very similar table is 4.3 in your textbook. Okay, so now let's go back. Previously, we talked about electron configurations of atoms. Okay, now we're going to talk about electronic configurations of ions. So let's look at an example. If we have sodium and we look at the electron configuration of sodium, sodium is element number 11, so it has 11 electrons. So we have 2, 4, 6 more to get 10, and then 11 electrons. The sodium likes to lose 1 electron. Okay, and which electron do you think it will lose? Well, it's going to lose electrons in the outermost valence shell because those are the easiest ones to pull off. And so if we pull off that electron to make sodium plus, if we write the electron configuration, it's just going to be 1s2, 2s2, 2p6, a full shell, which looks like neon. Okay, so that's the electronic configuration of neon, a noble gas. Okay, now on the other hand, if we have the chloride ion, so we take that electron from sodium and give it to a chlorine atom, okay, where are we going to add that extra electron? Well, there's one space open in the 3p orbit, and so we add that electron to give a full p shell. Okay, so we need to know how to write the electronic configuration of ions. Now, let's look at some atoms that are transition metals. Now, if you recall, when we're doing our electronic configuration, when we're filling electrons, we actually fill, say, the 4s orbital before we fill the 3d orbit. This is a little bit different in terms of, we're not filling the full principal quantum number 3 shell before we start filling some orbitals in the number 4 shell. However, when we start taking electrons away, we remove the principal quantum number 4, in this case, electrons first. And that's because they're further away from the nucleus than these 3d electrons. The 3d electrons just have more angular momentum, so they have a little bit higher energy. So those 4s electrons are the first ones that you remove. So if you're going to write the configuration for iron 2 plus, it actually is going to be this argon closed shell plus the 3d6 electrons. So we've removed the 4s2 electrons. Now, if you start pulling a third electron away from iron, so we've pulled those initial 2, the next electron does come from that 3d orbit. So for iron 3 plus, we have that iron core, we've removed the 4s2 electrons, and then we've removed one of the 3d electrons. Okay, so that's how you do electronic configurations of ions. All right, cool. Now, the next thing to look at is radii, right? So if we have the atomic radii of, say, the alkali elements, okay, they're relatively large, and they increase as we go down that column, which makes sense. Then if we pull off just one electron from each of those things, the radius shrinks dramatically. And the reason for that is we've removed all of the electrons from that last principal quantum number. So now we're just filling up shells that are the previous principal quantum number. So the radius, ionic radius of those things decreases dramatically when we've pulled off all of those valence electrons. Now, if we look at the alkali earth elements in the second column, you notice that you have to strip off 2 electrons to get that noble gas core. And when you strip off those 2 electrons, the radius decreases dramatically. Okay. On the other hand, if you give electrons to something like the halogens to gain this noble gas-like core of electrons, as we add the electron, the radius gets much bigger, as you'd expect. So this is the kind of the corollary argument. Now, let's look at the energy that's required to actually take these electrons away. So if we have sodium plus, right, how much energy is required to remove that electron? And we call this an ionization energy. So it's the amount of energy necessary to remove the highest energy electron from an isolated neutral atom in the gaseous state. Okay, so there's your full definition. And notice that it's positive for all elements, which means even if you have sodium that likes to give up its electron, its valence electron, relatively easy, it still takes energy. Sodium wants to hang on to that electron, and so you need to put some energy into that system in order to liberate the electron. So that's one thing to note, right? You still have to put energy into any element to liberate electrons. And you notice the noble gases have very high ionization energies, right? They do not want to lose electrons. And you notice as you go across a row, say going from lithium over to neon, generally speaking, the ionization energy increases as you go across that row. So it's easier to remove electrons one electron from atoms that are on the left side of the periodic table, because it's easier for those species to lose electrons and look like a noble gas rather than gain a bunch more electrons to look like a noble gas. Okay. Another thing that you notice is that if you look at the noble gases that are circled, as you go down that column, okay, the ionization energies decrease. And that's because as you go down that column, those atoms get bigger and bigger and bigger. So even though those noble gases don't really want to lose electrons, because xenon is so gargantuan, it's a lot easier to pull one of the valence electrons off of xenon, which has 54 electrons if it's an atom, than it is to pull one of the 2 electrons off of helium. Okay, so you see this decrease as you increase in atomic number. So the ionization energy goes down as the atoms get bigger. Okay, we can talk about multiple ionization energies, right? So that what we just discussed was what we call the first ionization energy, where you take some element or some metal and you put some energy in and you ionize that thing. So you have an ion and then an electron which can go somewhere. All right, well, you can have a second ionization energy where you take the singly charged ion, you add more energy, and you knock off a second electron and a third electron, and so on and so on and so on. Okay, and what you see is if you have a table of these ionization energies going from first ionization energy all the way down to knocking off the 7th electron, and you're looking at elements across the 3rd row of the periodic table, going from sodium over to argon. Notice for sodium, I knock off 1 electron. Okay, now it has no more valence electrons. If I want to knock off a second electron, tons and tons of energy are needed. Okay, and so these energies are in kilojoules per mole. Okay, so how many kilojoules of energy to ionize a mole of sodium or a mole of aluminum? Okay, and so notice the rough order of magnitude of these things. We're talking about hundreds to thousands of kilojoules per mole. So it's good to know that order of magnitude in terms of ionization energies. Okay, so sodium going from 1 to 2, huge step. All right, magnesium. Magnesium has 2 valence electrons. Both of those outer s electrons are there. And so we can take both of those off by putting in some energy. And then if we want to knock off the 3rd electron, huge jump to go to that 3rd electron. And you notice this stair step, right? Because for each of these species, as we go from left to right across this table, has 1 more valence electron. So you can notice that once we've removed all of the valence electrons, if we want to cut into that noble gas core, there's a huge jump when we cut into that core. So that's kind of an interesting thing to look at. Okay. Now, on the other hand, once we've ripped these electrons away from something, some atom, we can give those electrons to another atom. Okay, and the energy change that occurs when you add an electron to an isolated atom, that's called electron affinity. And notice these energies are negative, so this is kind of a goofy scale. It's increasing and negative, which means it's energetically favorable, right? So if I bring an electron around a fluorine atom, it's going to gain energy, right? That's an energetically favorable thing to do because that electron likes to interact with this positive nucleus in the fluorine atom. Okay, so that effective nuclear charge in that fluorine nucleus, okay, attracts this electron that we maybe can liberate from sodium or from some other element. Okay, so negative energies mean that it's energetically favorable. Okay. All right, and notice that some elements are near 0, right? So noble gases really are indifferent. They don't really care to add an electron or not, okay? But notice that most elements have negative electron affinities, meaning that it's energetically favorable. If there's a free electron just floating around, it'll take it, okay? And if you notice here, the highest electron affinities are for the halogens, okay? Because if they grab just 1 electron, they now have a full shell and look like a noble gas. Okay, so this brings us to what's called the octet rule, okay, which we've talked about quite a bit already, which means that these elements want to look like noble gases because noble gases have full shells of electrons, and that's energetically favorable. Okay, so if The alkali metals in general lose one electron. They then look like the preceding noble gas. If the alkaline earth elements lose two electrons, they look like a noble gas. On the other hand, if the group 6A elements or group 16 elements gain two electrons, they then look like a noble gas, and the halogens, and so forth. So that's the end game, is all of these elements want to have a full shell of electrons. An octet, okay, meaning 8, comes from full s and p orbitals, right? So for an s orbital, you can have 2 electrons. For a p orbital, you can have a total of 6 electrons. The sum of those is 8 electrons. So there's your octet. Okay, that's where that comes from. Full p and s shells. Okay. All right, now we're just going to quickly go over a little bit of chemical reactions that form ionic compounds. We'll talk about a lot more of this in detail in class. So let's start by looking at reactions of halogens and alkali and metals. Could be an alkali metal, could be an alkaline earth metal. Let's say it's an alkali metal like, say, sodium, right? So an example of this first reaction is sodium solid and chlorine gas. Okay, and we'll talk about why these. So why is this, a solid here? Why is this, X2? Why is there a 2 there? We'll talk about that later in class. But in general, that sodium, it's not too hard to grab that electron from it, and chlorine likes electrons very, very much. So the gain in energy of chlorine getting that electron from sodium is bigger than the energy that's required to grab it from the sodium in the first place. So this will make 2 NaCl's. And notice we have 2 metals to begin here and 2 chlorines, okay, to make 2 sodium chlorides, okay. Now, you can react these alkali metals with water to produce a singly charged ion in aqueous solution. So this is in a solution of water, and it produces hydroxide ions, which is on that table that you need to know, as well as hydrogen gas. And this is pretty explosive, this hydrogen gas, okay? And so there's a link here to a pretty sweet video of reacting alkali metals with water to produce a very explosive reaction. All right, alkaline earth elements behave in a very similar way to alkali metals. They're not quite as reactive. They like to lose 2 electrons as opposed to 1. And so they will again react with halogens, but being that each metal would somewhat readily give up 2 electrons, 1 metal is needed to react with Cl2 gas, for example, to make Mx2. So an example of this would be a calcium metal reacting with Cl2 to make CaCl2. Okay. In a similar way, alkaline elements also react with water to produce hydroxide ions as well as hydrogen gas. Okay, halogens, which are group 7A or 17, we've talked how they react with alkali metals and alkaline earth metals. These, we classify them as non-metals as opposed to classifying the alkali and alkaline earth metals as metals. These exist as diatomics in nature, as you'd find them in so-called elemental form, which is the name of if you find that element here on Earth by itself with nothing else around, what will it look like? Well, it's going to be a diatomic, generally gas. So fluoride will be F2, chlorine will be Cl2, and we'll talk about why that is later. These in elemental form are very reactive. And so in that case, when you find them in nature with other stuff, other atoms, you find them as salts or minerals bonded to other things because they're very reactive in their elemental form. Noble gases are very inert. They're happy. They have full shells. So they typically don't undergo a lot of chemical reactions. Okay, most of them exist all of them exist as gases. Yeah, they're very happy and not a lot of chemical reactions that happen with the noble gases. That ends what we're going to be talking about today, and I hope you learned a little bit.